to dive into the world of sinusoidal functions and their transformations. By the end of this video, you will be able to identify the amplitude, vertical shift, period, and phase shift of a sinusoidal function just by looking at its equation. Our main goal is to understand how to read these key features directly from a sinusoidal function. Sinusoidal functions are the backbone of modeling many cyclical phenomena, like waves, sound, and the changing seasons. The most basic sinusoidal functions are sine and cosine. Let's first look at the graphs of sine and cosine. Here's the graph of sine of x. It starts at the origin, reaches a maximum at pi over 2, and completes a full cycle every 2 pi units. And here is the graph of cosine of x. Notice it starts at its maximum value of 1 when x is 0. We can see the key points, the zeros, the maximums at 1, and the minimums at -1. Both functions have a period of 2 pi. Notice how they are essentially the same shape, just shifted. The cosine function is simply the sine function shifted to the left by pi over 2 units. This means that any transformation we learn for sine will also apply to cosine in a very similar way. The cosine function is just a phase shift of the sine function. Now, let's explore how we can change these basic graphs. We do this through transformations, which can be additive or multiplicative. We'll focus on additive transformations first. These transformations shift the graph without changing its shape. The first additive transformation is a vertical shift. The equation for this is f of x equals sine of x plus d. Here, d determines the shift. If d is positive, the entire graph shifts up. If d is negative, it shifts down. The most important feature that changes with a vertical shift is the midline of the function. The midline is the horizontal line halfway between the maximum and minimum values of the graph. For the standard sine and cosine functions, the midline is the x-axis, or y equals 0. The equation of the midline for f of x equals sine of x plus d is simply y equals d. So, the value of d tells you exactly where the new midline will be. The second additive transformation is a horizontal shift, also known as a phase shift. The equation for this is f of x equals sine of the quantity x plus c. Be very careful here. The shift is not c, but negative c. This is a common point of confusion. A positive c inside the parentheses means the graph shifts to the left, and a negative c means it shifts to the right. Think of it as doing the opposite of what you'd expect. Let's see this in action. If we graph y equals sine of x plus pi over 4, the graph of sine of x moves to the left by pi over 4 units. Conversely, if we graph y equals sine of x minus pi over 4, the graph moves to the right by pi over 4 units. So, the phase shift is negative c. It's a horizontal translation of the graph. Now let's move on to multiplicative transformations, which change the shape or scale of the graph. The first is the vertical stretch or shrink, which affects the amplitude. This transformation has the form f of x equals a times sine of x. The amplitude, which is the distance from the midline to the maximum or minimum, is given by the absolute value of a. If the amplitude is large, the graph is stretched vertically. If it's small, it's compressed. It's the absolute value because amplitude, being a distance, must always be positive. A negative a value doesn't change the amplitude, it just reflects the graph across its midline. Here you can see the difference between y equals sine of x, y equals 2 sine of x, and y equals 1/2 sine of x. The amplitudes are 1, 2, and 0.5 respectively. The second multiplicative transformation is a horizontal stretch or shrink, which affects the period. This transformation has the form f of x equals sine of b times x. Remember, the period is the length of one complete cycle of the function. For standard sine and cosine, the period is 2 pi. The value of b changes that period. The period is calculated as 2 pi divided by the absolute value of b. Just like with phase shifts, b works in the opposite way. If b is greater than 1, the graph is compressed horizontally and the period becomes shorter. If b is between 0 and 1, the graph is stretched horizontally and the period becomes longer. Let's compare y equals sine of x, which has a period of 2 pi, to y equals sine of 2x, which has a period of 2 pi over 2, or just pi. We can also look at y equals sine of 1/2 x, whose period is 2 pi divided by 1/2, which is 4 pi. You can see that a larger b value makes the cycles repeat more quickly, and a smaller b value makes them repeat more slowly. Now, let's put it all together into one single powerful equation that incorporates every transformation we've discussed. This is the general form of a sinusoidal function. Y equals A times sine of the quantity B times the quantity x plus c, all plus d. All four parameters are here. Let's recap what each parameter tells us about the graph. The coefficient A gives us the amplitude, which is the vertical stretch or compression of the graph. It's the absolute value of A. The parameter B determines the period, which is the length of one complete cycle. The period is found by taking 2 pi and dividing it by the absolute value of B. The parameter C gives us the phase shift, which is the horizontal translation. It's important to remember that it's negative c. If c is positive, we shift left. If c is negative, we shift right. Finally, the parameter D gives us the vertical shift, which is the vertical translation. It also defines the new midline of the function, which is the line y equals d. By understanding these four parameters, you can describe the graph of any sinusoidal function, no matter how complex the equation looks. Let's work through an example to see how to apply these rules. This will give you a clear, step-by-step process. Consider the function y equals 3 sine of the quantity pi over 2 times x minus pi, all minus 1. Our goal is to identify the amplitude, period, phase shift, and vertical shift. First, the amplitude. This is the absolute value of the coefficient A, which is 3. So the amplitude is 3. The amplitude is 3. Next, the period. For this, we need B, which is the coefficient of the factored x. Looking at the equation, B is pi over 2. So the period is 2 pi divided by pi over 2. This simplifies to 4. The period is 4. Now for the phase shift. The phase shift is negative c. In our equation, after factoring out pi over 2, we have x minus 2, which means c is minus 2. Therefore, the phase shift is negative minus 2, which is positive 2. This represents a shift of 2 units to the right. The phase shift is 2, indicating a shift to the right. Finally, the vertical shift. The vertical shift is given by d. Here, d is minus 1. So the graph is shifted down 1 unit, and its midline is y equals minus 1. The vertical shift is minus 1, and the midline is y equals minus 1. To recap, for the function y equals 3 sine of the quantity pi over 2 times x minus pi, all minus 1, we have an amplitude of 3, a period of 4, a phase shift of 2 units to the right, and a vertical shift of 1 unit down, with a midline at y equals minus 1. Let's try another example, this time using a cosine function to show that the process is the same. Consider the function y equals minus 2 cosine of the quantity 3x plus pi, all plus 4. First, the amplitude. A is minus 2, so the amplitude is the absolute value of minus 2, which is 2. The amplitude is 2. Second, the period. The coefficient of xb is 3, so the period is 2 pi divided by 3. This means the cosine wave completes one cycle in 2 pi over 3 units. The period is 2 pi over 3. Next, the phase shift. Before we can identify c, we must factor out the b value from inside the parentheses. So, 3x plus pi becomes 3 times the quantity x plus pi over 3. In this new form, c is positive pi over 3. The equation becomes y equals minus 2 cosine of 3 times the quantity x plus pi over 3, all plus 4. Now we can find the phase shift, which is negative c, so it's negative pi over 3, representing a shift of pi over 3 units to the left. The phase shift is negative pi over 3. Finally, the vertical shift is d, which is 4. The graph is shifted up 4 units, and the midline is y equals 4. The vertical shift is 4, and the midline is y equals 4. In summary, for y equals minus 2 cosine of the quantity 3x plus pi, all plus 4, we have an amplitude of 2, a period of 2 pi over 3, a phase shift of pi over 3 to the left, and a vertical shift of 4 up, with a midline at y equals 4. So, let's quickly review the key takeaways from this lesson. Understanding these concepts is essential for working with sinusoidal functions. We learned that the general form of a sinusoidal function helps us identify all the transformations at a glance. This general form is y equals a sine of b times the quantity x plus c, all plus d. We also learned how to use the parameters in this equation to calculate the key features of the graph. The amplitude is the absolute value of a, the period is 2 pi over the absolute value of b, the phase shift is negative c, and the vertical shift is d, which is also the equation of the midline. You are now able to look at a sinusoidal equation and determine its amplitude, period, phase shift, and vertical shift. These transformations allow us to model a vast array of real-world phenomena. Thank you for watching.